Hi, this is the fifth free response question on the AP Physics C extra credit, and it's the final video I'm going to make because I did all the multiple choice questions first. And this is the last FRQ, so let's make it a good one. So here we're given a function that it shows potential energy with relation to displacement. And the physics facts we're going to need to know are our classic conservation of energy. Mechanical energy is conserved when there's no net work done by external forces. And here, only conservative forces act on the object. So that applies to us. And then also, we're going to need to know that the area under a force versus displacement graph is work. Right. Okay, so let's get into it. Due to energy constraints, the object can only move between x equals -1 meters and x equals 1 meter. What is the total mechanical energy of the system? Well, let's plug in -1, u of -1, and that's going to be 10 over 2 equals 5, and u of 1 is going to be 10 over 2 equals 5. Okay, so now, using our knowledge of energy, we can determine that the total energy of the system is 5 joules. And that is because, since the subject is only conservative forces are acting on the object, the total mechanical energy is constant. And then this is the sum of potential energy and kinetic energy. So the maximum potential energy in the system would be at these 2 points, because the kinetic energy at these 2 points would be 0. Because it says the object can only move between x equals -1 and x equals 1. So it's out of kinetic energy. So that means it's all potential energy here, and our potential energy is 5 at both of these points. So our total energy of the system would be 5. So our answer to A is going to be 5. And that's our justification. Okay. Now, B. The object is released from rest at x equals -5, moves in the positive direction, and passes through x equals -1 meter. Explain how object speed travels as it goes from x equals -5 to x equals -1. Well, u of -5 is 10 over 26, which is about 0.385. Let me double check that. I did that before. Yeah, 0.385 joules, and u of -1 is 5, as we said before. It's 5 joules. So since the object is released from rest, the kinetic energy is 0 at x equals -5. So K E equals 0. So our speed at x equals -5 is 0. Because our equation for kinetic energy is 1/2 mv squared. M can't be 0, so v would have to be 0. So as the object moves from -5 to -1, the potential energy is increasing. So, and since total mechanical energy is conserved, an increase in potential energy would mean a decrease in kinetic energy. So the object's speed would decrease as it approaches x equals -1. Okay. Now let's go to problem C. Explain how the object's acceleration changes as the object travels from x equals -5 to x equals -1. Well, here's where that work physics fact is going to come in. The area under the curve of force displacement is work. Well, our work here, that just means work. Yeah, area under the curve is just integral. We know that as physics C students. And then our work is just going to be our change in U. And it's going to be a negative change in U. That negative shows that the object follows travels where potential energy is decreasing. So negative change in U equals f dx, and then we can simply take the derivative of each of those, and we figure out that force is equal to negative d over dx u of x. So that's our force. So let's take the derivative of our equation. Yes, we have to take the derivative. So I just wanted to see if we could calculate the slope if it was a straight line, but it is not. So d So I did this before, so I'm not going to show all the steps, but you're going to use quotient rule, and you take derivative, so 0 minus 20x over x squared plus 1. And then so it'd be negative 20x over x squared plus 1 squared. And that's just going to be 20x. 20x over x squared plus 1 squared. So now, and this is our, so this is our force. And our force, using Newton's second law, force equals ma. And so then you can figure out, this equation equals 2, because it's given it's a mass of 2, equals 2a. So our a equals 20 over 2 squared plus 1 squared. So now, if we calculate it at a of x, I should say. And if we find a of -5, we find that it's about -20x, sorry. We inputting in my calculator, and we find that it is negative 0.074. Okay, and then if we plug in a of negative 1, just again plug it into your calculator. Don't waste time doing it by hand. That's what I'm just plugging it in. We find, and this one's much smoother, and this is negative 2.5 meters per second squared. So what this tells us is that as the object travels from negative 5 to negative 1, the magnitude of acceleration is increasing. So acceleration is increasing in the negative direction. Okay. Now let's go to D. So D asks, what is the farthest position to the left and farthest position to the right that the object can reach? Well, what we need to do here, we calculated before, total mechanical energy is 5. We've asserted that. So if total mechanical energy is 5, an object cannot go pass any further than when its kinetic energy reaches 0. Its kinetic energy reaches 0 when the mechanical energy is purely made up of potential energy. So we got to find, when is u of x equal to 5? So we do that. We set 10 over x squared plus 1 equal to 5. And then 5x squared plus 5 equals 10. And then we're going to get x squared equals 1. X, and shocker, x equals plus minus 1. That's what we were given at the start. The max distance is x is, the distance is x is, the object is constrained by. It can't go past positive 1 or past negative 1. So it's has to stay between negative 1 and 1. And we just proved that. And finally, for question E, this is one I was kind of confused on, and I used something Mr. Scopetis told me to do. He's like, consult ChatGPT if you're confused, as it's super helpful. So I asked it, I go, how would you use a potential energy and displacement function to locate a point of stable equilibrium? And it described that a local minimum of the function would represent a point of stable equilibrium, because a local minimum would show that at that point, if it's slightly displaced, the object would experience a restoring force that pushes it back towards the equilibrium position. So it doesn't ask us to find the points, but it just asks us to explain how for a different u of x we could use it. So we would just find u prime, and we actually already did that for ours, but you would find u prime of x, and you would set it equal to 0. And set u prime of x equal to 0. You would find the points where u prime equals 0. Let's say it's at x, let's say u prime equals 0 at x equals 2 and negative 2. Well, then you would plug in a value smaller than 1, they're smaller than 2, and a value larger than 2. If the value smaller than 2 is negative and the value larger than 2 is positive, it's a local min. And that's called our first derivative test, because u prime went from negative to positive. And then you could do the same thing with the negative. So our local minimums would be our points of stable equilibrium. So that's the last FRQ. I really enjoyed doing these problems, and I Thank you for watching.